Hi everyone, this is Ms. Rosita. We're looking at Chapter 4, Section 2 today, talking about inverses. So first off, just to make sure people have a basic level of understanding of an inverse function, I'll give you a quick example. If you take some number, any number you want, and you square it, and then you square root it, you should get your number back. So squaring and square rooting are inverses of each other because they basically undo the other function. One of them undoes the other one. I could say x plus 2 and then turn around and say minus 2 and I'll get x back. So backwards and forwards. So here we are looking at, I guess, a little bit more specifically what is an inverse function. So they start us off talking about inputs and outputs, showing these mappings here. So for the first one, it says we have 1, 3, and 5, and those are mapping to the numbers 2, 4, and 6. Okay, so whatever function is doing this, it looks like basically we're just have some sort of function that adds 1 to our input to get the output. Well, on the output to input, or I guess these ones, they switched the top here, input and output. Basically, they're just changing the direction of the arrows. So if I start with 2, 4, and 6, this time, and I subtract 1 from each of them, I'll get 1, 3, and 5. So adding 1 in the first column, or adding 1 in the first set of mappings, and subtracting 1 in the second set of mappings, adding and subtracting by the same amount, that would be basically undoing each other. Those are inverses. So when the direction of the arrows switch, from going to the right to going to the left, that's basically our inverse. Okay, so let's see. They talk about mappings here. I think I'll just skip that. You can read that on your own. Oops, I'm sorry. Trying to figure out where my cursor is. There we are. Okay. So if I scroll down, let's look at the reflect question. Oh, actually, before that, I do want to talk about the notation here. So right above the reflect statement, it has the notation f with a little exponent, -1. So here, this -1 exponent is the inverse notation. So when you see f of x as a function and you want to know what the inverse of it is, we would write it as f with a little exponent of a -1 of x. So you'll say f inverse of x is how you pronounce that. I should mention that little -1 exponent. I know a lot of you are clear that exponents that are negative usually means throw it in the denominator or take the reciprocal. That is really nothing to do with inverse functions. So it's a little confusing notation when you have an exponent that could mean really literally an exponent, like a -1 would be a reciprocal, but that really isn't what we're talking about with inverse functions. It has nothing to do with reciprocals. It's just the notation that we use. So when you see a -1 exponent, we're going to think of that as the inverse of f. Okay, so let's move on to the reflect. It says, how do you know that each mapping diagram shows a function? Okay, so they're trying to get us to remember what exactly is a function. So a function basically needs to pass a vertical line test, which means that when you plug in any number for x, you only get one number out for y, not two different values. So as long as each value of the inputs goes directly to one value in the output, we can call it a function. You wouldn't want to have a number in the input with two arrows coming out of it going to two different places. That would not be a function. So how do we know that each mapping diagram shows a function? Well, because each input goes directly to one output, not more than one. Okay, part B, the domain of the function f of x, if the domain is 10, 20, and 30, what does this information tell you about f inverse of x? Well, the domain of f turns into the range of y. So the input for one is the output for the other. So again, the input for the original function is the output for the inverse function. Okay, so domain and range are switched. If the graph of a function f of x includes the point 3, 0, what must be the graph of f inverse of x? Or what point must it include? Sorry, I can't read. So 3, 0, well, since the input and output are switching, then it would become 0, 3. Okay, so in general, I put there in parentheses at the bottom that x and y are getting reversed. So whatever was x before is now y, and whatever was y is now x. Second explore here, it says finding f inverse of x using inverse operations. Okay, so now we're interested in actually getting what the inverse function equation is. So they're going to start us off with f of x being 3x minus 2. And we're going to try to figure out what f inverse of x would be. So in part A, they say describe the sequence of operations performed on the input value of x for the function. So just kind of thinking about what 3x minus 2 does. First, you would take your value of x and multiply it by 3, and then you would subtract 2. Pretty straightforward stuff. So when you want to do the inverse of this, you basically have to kind of reverse this. It says for part B, describe the inverse of each operation listed in step A, but in reverse order. Okay, so we're doing the inverse. So the last thing what we had done was subtracting 2. So this time we're going to add 2. And then the first thing that we had done was multiplying by 3. So this time we're going to divide by 3. We're doing the opposites, trying to undo the original function's work to get the inverse function. So if I take value of x on the inverse function, I would need to add 2 and then divide by 3. And so my inverse function would be x plus 2 over 3. So that would be the inverse of 3x minus 2. Okay, so if I drop down to the tables, they say go ahead and compute our input-output tables. So in our original function f, if I plug 0 in for x, 3 times 0 minus 2 is negative 2. And then 3 times 2 minus 2 is 4. And 3 times 4 minus 2 is 10. And 3 times 6 minus 4 minus 2 is 16. So this is my input-output table, or my x and y table for my original function f. Then the inverse, if we're clear that really what we're doing is just changing the direction of the arrows and those mappings, then that means my inputs will be what were the outputs. So my x and y's have basically just reversed. So compare my second table to the first table. You'll see the second column is now the first column and vice versa. Okay, so going to the reflect, it says, explain how the tables show that you found the inverse of a function correctly. So if I had actually plotted all my points in the table rather than just flipping them around, if I had truly plugged them into the equation, I would see that, in fact, I do get that the x and y's have been reversed. So why do you reverse the order of the steps when you're writing them? Well, when we're undoing the operations in the original function, you really do have to go backwards. I guess I didn't really explain why, but you're trying to undo the operation. Okay, so if you're adding, the opposite would be subtracting, and you have to also go in the backwards order. So the last thing that you had done is now the first thing that you do. So it says, could the rule for f inverse of x be written as 2/3 plus 2, and explain why or why not? And the answer is no, because if you write it as x over 3 plus 2, then that would mean that you would be dividing by 3 first and then adding 2. But actually what we wanted to do was add 2 to x first and then divide that whole expression by 3. So we wouldn't get the same thing if we divide first and then add. We need to add, then divide. Okay. So it says finding f inverse by solving an equation. So rather than trying to think about working backwards to get this inverse function, there's another way of doing it. So basically they say, okay, well, instead of calling it f of x, let's just simplify it and call it y. So that's our first step. And then if I want to get the x by itself, I'm going to go ahead and add 2 to both sides of the equation and then divide by 3. And this expression, if you're looking at it, looks very similar to what we said on the previous line. The only thing is that x and y need to be reversed. So in other words, if I'm trying to have, like they give me f of x and I'm looking for f inverse of x, then what you can do is isolate x, get it by itself, and then just switch x and y, the actual letters. So down here below it says write the rule. Well, it would be x plus 2 over 3 equals y. And y is, of course, what our new function is, f inverse of x. So my personal preference on doing this, because a lot of the times this is a pretty standard question where they'll say, here's a function f of x, find its inverse equation. What I personally find easier is I like to switch my x and y coordinates first. So instead of y equals 3x minus 2, I'll say x equals 3y minus 2, and then I just get the y by itself. So add 2, divide by 3, and then I'm done. I just have to remember that I've already switched my coordinates, so this y is actually f inverse of x. So that's a pretty standard process to try to figure out what the inverse function is for the equation. Okay, so a couple reflects. How are the steps of solving the, whoops, uh-oh, what did I do? Sorry, back up a little bit. How are the steps of solving the equation in part A similar to what you did when you wrote the inverse operations? Well, both times you would add 2 first and then divide by 3. It's the same thing. Why does it make sense to switch the variables when writing the inverse function? Oh, because the input and the output are reversed, right? The two columns of our table get reversed, or the original mappings that we started the discussion with today, the arrows on the mappings got reversed in terms of their direction. Okay, graph a function and its inverse. So still sticking with the 3x minus 2 function that we've been looking at, go ahead and graph that. I did that in black, and notice the y-intercept is -2 and the slope is 3. So go ahead and draw that in. And then it says, okay, well, how about the f inverse function? What does that one look like? So we said the equation after we looked at it a couple times was x plus 2 over 3. And I can rewrite that if I want to call that x over 3 plus 2/3, or 1/3 of x plus 2/3. So anyway, I would go to 2/3 on my y-axis and then use a slope of 1/3, up 1 over 3. And I draw in my new picture. It's a line here with the y-intercept of 2/3, and I labeled it f inverse of x. Now, when you're looking at the picture, this goes on to part C on the next page. Looking at the picture, if I draw in the line y equals x, just the line with a slope of 1 going through the origin, I notice that the red line and the black line are a reflection of each other across that line y equals x. In other words, if I were to have folded my paper along the line y equals x, the black line and the red line would basically be on top of each other when I fold the paper. So yeah, these functions are definitely symmetrical across the line y equals x. And that's what this reflect is asking. So it said, first describe the relationship between coordinates of the points of the graph on the function and those on the other one. So the x and y are reversed, if you notice the coordinates. And then part B, it says to draw that line that I made dotted, y equals x, and then talk about what the transformation was. And we said it was a reflection across that dotted line. So again, that first one, when it was talking about the coordinates getting reversed, if you're thinking about two functions, we said the inputs and outputs get reversed. So in terms of the picture, if I think of a point, let's say, how about this point on the original function f that's at 0, -2? The new function then, instead of having a point 0, -2, it should be -2, 0. And sure enough, if you look on the red line, -2, 0 is sitting right there. So xy and yx, they're getting reversed. It's a reflection across that dotted line, but also the x and y coordinates are getting reversed. So if I'm looking at a function f graphically, and maybe I don't even know what the equation is, I should still be able to draw the picture of the new function just by reversing the coordinates and plotting some new points and sketching it in. Okay. So then they go on to this kind of discussion in here about real-world functions. Okay, so when you're talking about the inverse of something in the real world, it wouldn't actually make sense to switch the x and y values because x actually means something and y actually means something, and you can't just switch them. Okay, so they say if you're trying to find the inverse function, you're still going to isolate the other variable, get it by itself to get the new equation. Just don't switch x and y at the end because x and y actually have meanings. So it probably makes a little more sense if I just go straight to this example. So it says Mr. Williams is driving on a highway at a speed average 50 miles per hour. Destination's 100 miles from there. And here's the equation. Distance is 100 minus 50t. So t is going to be our time in hours, and 100 is because you start off 100 miles away and you're going to subtract your rate, which was 50 miles for each hour t. Okay, so it says write and interpret the inverse of this function. So first of all, if I want to write out what the inverse is, I basically get my t by itself, which means I'm going to need to move the 100 over to the other side and then divide by -50 to get the t by itself. And I simplified it. 100 over -50 would be -2, but it's d minus a -2, which is really a +2. So, so here's my equation that I end up with. And oh, I guess just to be careful on the signs, d is over negative 50 as well as the negative 100 being over negative 50. So make sure you're dividing correctly there. Both terms in the numerator get divided by the denominator there. So here's our new equation. And again, usually we isolate the other variable and then we would switch the x and y or switch the d and t. But because d and t actually have a meaning in terms of this word problem, we don't really want to switch it. So we're just going to leave it time is equal to something in terms of distance. So interpret the inverse function. So again, time t, sorry, it's kind of poor handwriting there, it's supposed to be a t. Time t is in hours. And again, the distance is what they're calling d, which is in miles. Okay. Where's my cursor again? I'm always losing my cursor. There we are. Okay. So last little bit here. Another reflect. It says use the inverse function to find the time that Mr. Williams has left to travel after he's gone 75 miles. So our time is equal to 2 minus the distance over 50. That's what we just got above in the previous line. So if our distance is 75, I plug that in, simplify it, and it looks like he's got a half hour more of driving time. Okay, that was the whole thing, your introduction for inverse functions. So kind of just recapping real quickly here. One is you'll need to make sure that you're clear how to find the equation of the inverse. And the other is you want to make sure that you understand how to graph the picture of the inverse. So again, to get the equation of the inverse function, I suggest you switch x and y first and then just get the new y value by itself. And at the end, call y f inverse of x with a little -1 notation, exponent. And then the graph, remember if you're looking at a picture of a function, to get the new graph of the inverse function, you just think of all the points that on the original picture that you have and switch the coordinates. X and y becomes y and x. Plot your new points, you've got your new picture. That's really all there is to inverse functions. Thanks so much. I will see you soon.